Okay, so here's where we were last time. We were talking about level sets, and we had just kind of barely gotten started, as I recall, with level sets. So big picture idea, make sure to remember a level set. Boring color there. A level set it's a pre-image, right? So a level set is specifically, it's the set of input values to the function that gives you a prescribed output value. Okay, so we saw an example. This is where we ended it last time until we've got a specific function here. And if you look at this output value 1, and if you ask what are the input values, what are the x and y, right, that when I plug them into the function being x squared plus y squared, give me this output value 1. Right, and so if you take this equation then and solve for the x and the y, that gives you that circle right there. So this is one of the level sets, or because it's a curve, we call it a level curve for that function. And you can plug in different output values that give you different equations, which then give you different curves. Okay. All right, so a little bit of intuition. I claim that many of y'all have actually already seen level curves, might not have thought of it in those terms at the time, but if you've ever looked at a topographical map, either from a hiking experience or whatever, if you have the contour option on Google Maps and it's set at just the right zoom level, they have little contour lines that pop up that show you kind of the shape of the terrain. And in fact, each one of these contour lines represents a single altitude. So, for example, this contour line here might be, altitude equals 300. I don't know, something like that. Notice that is a level set. It's literally where there is a function, in this case altitude, that we are setting equal to a constant and then looking for what the inputs to the function are that give rise to that set output altitude, right? So level sets of the altitude function, and let's see here when I do it like this, the altitude function, and these are level sets because I'm setting that function equal to a constant. Everybody on board? So now, is this the world's best way to understand a function geometrically? Look, it has its moments. There are certain nice things about a level set. In a situation like this, this contour map that I've got drawn here, there's one kind of nice thing about it in particular. I can see that it's really steep along in here. Because if you just think about it, each one of these contour lines might, for example, represent, let's say, 100 feet of altitude. Well, wait a second, then going from here to there, it doesn't look like I went very far. Horizontally, I did not cover a lot of distance, and yet 1, 2, 3, 4, and apart. That's like 450 feet of elevation gain over a pretty short horizontal distance. That means that's really steep. Right? Whereas that same amount of distance over here, well, golly, that's barely any altitude change at all. I mean, it's hard to tell exactly, but if one were to ballpark, you might speculate this is somewhere in the range of around 50 feet or something, right? So much less steep here, much more steep there. How close the contour lines are together, in some sense, tells you how steep it is. So good geometric information that you get out of what is, in fact, a pretty simple picture to draw. It's a two-dimensional picture, for one thing, right? If I were to try to draw a graph of this function, well, there's 2 input variables, there's 1 output variable. That's a total of 3 variables. That means I would have a 3-dimensional picture. The graph of the altitude function, actually, kind of, if you will, technically, it's kind of the mountain itself is a graph of the altitude function, right? And that's just being a 3-dimensional thing, a lot harder to carry around on a hike. That make sense to everybody? Okay. All right, so nice benefits there. Here's a neat fact. Let's think about a function of 2 variables again. And again, we have a couple of different constructions we can talk about. We can talk about the graph, where we set the values equal to a new variable z. We can talk about level sets, curves in this case, where we set the value of the function equal to constants. These are two totally different constructions. Right? And again, we're going to have, in some situations, we're going to need to talk about graphs. In some other situations, we're going to need to talk about level curves. These are different. They're dimensionally different, in fact. This one, after all, you look at the graph equation here, there's three variables. This is a three-dimensional picture, which is weird because it's a function of only two variables, right? But nevertheless, three-dimensional picture. Level sets, not. This is an equation of only two variables. There is no z in the level curve picture, right? So dramatically different kinds of pictures, and yet there is a relationship between them, and this is a beautiful little observation. If you take your graph, right, and to that graph, if you then take what I'm going to call a horizontal cross-section, and let's think about this for a second. I say z equals c, means you're taking a horizontal cross-section. This is the equation of a plane, right? Z equals a constant. It's a horizontal plane. And so insisting that both of these equations be true means I'm looking for points that are on my graph, but that are also in this horizontal plane. In other words, I'm looking for the intersection of my surface and my horizontal plane. That's a cross-section. Notice it's morally equivalent to this level set, because after all, if f is equal to z and z is equal to c, then altogether, it's basically saying f equals c. Everybody with me? All right, let's draw a picture. See this in action. Alrighty. Here's a multivariable function, two variables. Setting it equal to a constant to give me level sets. Various different constants I could plug in here, but notice this is always going to give me a circle. Right? So what I get here is a bunch of concentric circles. They're all centered at the origin. Yeah, something like that. Okay, fine. What's the graph look like? The graph, now we aren't really quite prepared to look at this equation and immediately infer what this is an equation of. We'll get to that actually in just a few minutes. But again, a graph is what you get when you set the function equal to z, a new variable that is. In this case, I'm going to use z. And I claim, again, we'll see why in just a minute, I claim that this is a bowl-like shape, kind of like this. Now, again, let's take a moment to recognize how different these pictures are. Very different. Totally different kinds of pictures. These are curves. That's a surface. Completely different kind of critters. They live in different worlds. This is in 2 dimensions. This is in 3 dimensions. Completely different things. And yet, related? Because again, if we were to take cross sections, setting z equal to various different constants, like that. And here's some horizontal cross sections, and I appeal to your geometric intuition. What happens when I take a round bowl and I take horizontal slices like this? And well, what I get are concentric circles. We get exactly level sets. I mean, lifted up out of the plane, yeah, sure, to be fair. The level sets themselves live in 2 dimensions. These cross sections of the graph technically live in 3 dimensions, but if you look at the XY relationships on these cross sections, they are the exact same XY relationships as in the level sets. Okay, so that's the connection. Nice little relationship there. Okay, moving along. I've made this observation before that in Calc 1 classes and Calc 2 classes, you could pretty much get away with treating every picture as being a graph because you don't really need any other pictures. The graph kind of does it all in some sense, and they're convenient to represent. They work out great on paper. You couldn't ask for a better kind of picture. But not so in multivariable. So we're going to have multiple kinds of constructions running around, and for any given function, there's its graph, there's its level sets, various different pictures that we can draw, right? Let me point out you can turn that around. Instead of thinking about a function and asking what are the different pictures I could draw, you can say, if I have a picture such as a line, if I could draw the line, oh, come on. There we go. Line, given an equation. What are the various functions that I can claim that this relates to? Is this a graph of something? Is this a level set of something? I'm going to also ask while we're here, is this parameterized by some function? Right? And here's the thing, we're going to be eventually learning pretty soon now, coming, in fact, possibly even later today, we'll see. What I'm going to call geometric interpretations of calculus. What does a derivative look like? Right, a multivariable derivative. Is it like the slope or something? Right? What's the geometric take on it? And the answer to that question is going to depend on what kind of a picture you're looking at. So if I want to understand this line from the point of view of the calculus of graphs, I need to be able to identify exactly what function is this the graph of in order to apply the calculus of graphs. On the other hand, if I want to understand this line by using the calculus of level sets, I need to find a function for which this is a level set. If I want to use the calculus of parameterizations, I need to find a function that parameterizes this line. Right? So, and they're all different functions. So here we go. Let's talk about these different functions. I claim here that, let's see here, I would use green here. And this right here is a function, what I have in green, that's the function whose graph is this purple line. Now, how do I know that's true? Well, keep in mind what a graph is. Whoops, I wanted to be in pencil mode here. Keep in mind what a graph is. A graph is what you get when you take your function and you set its values equal to a new variable. Oh wait, this is a function of only x, so I can set this output value equal to y. The graph is this equation that I get when I set the function equal to y, and notice that is equivalent to that purple equation. You gotta move things around a little bit, no big deal, but they're equivalent equations, exact same solution sets. And so literally, this function has its graph that has the exact same equation. In other words, this line is the graph of that function. Is everybody with me? Now, where did I get it from in the first place? Right? Did I just pull this out of a hat? Did I consult my inner oracle? How did I come up with 6 minus 2x over 3? Right? And the way you're going to find what this function is basically to kind of work backwards through the argument that I just made here. Given this function, I set the value equal to y and then do a little algebra. Working backwards, I can say, all right, this y, apparently I just need to solve for it. And it's as simple as that. In this equation, solve for y, that gives you the function whose graph is your curve. Everybody with me? All right. Now, let's talk level sets. Let's see here. There we go. I claim, and this is an easier one, I claim that this is a function for which one of the level sets is my line. And this, again, this is a lot easier to see because let's just do it. I mean, how would I take a level set of this function? Well, level set means I'm going to set this equal to a constant, and I can set this equal to any constant I want. I'm going to choose 6, right? And then, sure enough, I end up with not only an equivalent equation, right, but I end up with literally exactly the same equation there. So that was easy. Okay. So how do you find this function? Well, again, this happened to be obvious in this case. But what I needed out of this purple equation to be able to produce this function is I needed it to be in the form of stuff equals constant. And that's just not hard to do, right? Whatever you have in your equation, just kind of whip everything over onto the left-hand side, except for maybe a constant. If you want to leave a constant over there, it doesn't matter. Go ahead, and then, bam, you're in the required form. Everybody good? Yeah.
So, it's the pre-image of 6. Is it like?
Yeah, that's right. That's right. So looking at this function g, defined by this formula, this line is the pre-image of 6 in the sense that everything on this line, when you plug it into this function, will output 6. That's right.
So the function g is like the inverse of another function, like when we because.
No, I mean I hear where you're coming from, and like the notation that we use for level sets actually has the little inverse in it. The problem is these functions usually, almost always, are not invertible. And so, yeah, it's an abusive notation. It's technically not. There is no inverse function, but it's, given an output value, we want to kind of work backwards to figure out what the input values were that would give that. So, I mean, there is this kind of inverseness-ish of it, right? But it's technically not invertible. Yeah. Yes.
For a function to be invertible, do the input and output have to have the same dimension?
Yeah, that's right. Yeah. Oh, well, I mean, oh, God, let me think now. There might be some really weirdo, obscure counterexamples that are nowhere continuous or some, really strange stuff like that. But yeah, generically, day in and day out, Math219, yeah, totally. Yeah, right. Yeah. All right. Okay, so let's suppose that we know the calculus of graphs. And by the way, we will pretty soon, right? If you encounter a question that says, hey, here's a line, and they give you this purple equation right here, and you know that it's this purple line right here, and if you want to use the calculus of graphs, how would you apply the calculus to what would you apply the calculus of graphs? Which function do you do the calculus of graphs to? Well, you do the calculus of graphs to the function whose graph is the line that you're interested in. And if you apply the calculus of graphs to this function down here, that's a mismatch, right? That doesn't make any sense. You're applying the calculus of graphs to a function for which it's one of the level sets that gives you the curve, and it doesn't make any sense. So make sure this is a deceptively subtle and dangerous little moment here. Because a lot of students will look at this and think, there's barely even any algebra in that, right? The hardest thing that happened here was somebody divided by 3, right? It was the algebra here is trivial. But it's the delicacy, it's the strict, proper interpretation of the words and applying tools to functions that they apply to, right? And just, it's the being careful of it all that makes this hard. And that makes this delicate and therefore dangerous. So super careful. Make sure to use these terms strictly, properly, and then you'll be okay. Last observation I'll make is that there is this third function down here, and this function right here parameterizes our line, and we can. And by the way, how I came up with this parameterization is kind of a chapter 1 exercise, so you can notice this line as given. There's a point I can see right there that's on this line, and I can make a direction vector by subtracting these 2 points, right? And combine them a la chapter 1 into with a parameterization like this. And it's going to turn out that there will be a calculus of parameterizations that will tell us a third kind of type of information about this line, also useful in different circumstances. Okay, so again, don't try to apply the calculus of parameterizations to this function. It doesn't make any sense, right? Total mismatch. All right, so careful with all of that. That's basically what all this says. So I'm going to move along. Here's a scenario that comes up more often than you'd think. I'm going to start with this algebra right here, which is really easy algebra. Right? Look, hardly anything happened there. All I did is I took the right-hand side and I subtracted it over to the left-hand side. Barely anything happened. And it turns out that this little bit of algebra is actually really useful. As follows. The top equation is a graph. Right? Y equals a function of other variables. I've taken a function and said its output value is equal to a new variable y. This is literally a graph. This is the graph of this function right there called f. Okay. What about the bottom equation? The bottom equation is literally a level set. Right? I'm literally taking some expression and setting equal to a constant. In this case, 0, whatever. And so the bottom equation I can interpret as being a level set specifically of that function. Everybody with me so far? So the reason we care about this is what this means is if I find myself looking at a graph, and again, this comes up surprisingly often. If you're given a function and the question says, hey, think about its graph, that's going to happen. Then you find yourself looking at this equation, and it may be that for your needs at the time, the calculus of graphs, what you can infer by doing calculus on this function f might just not tell you what you want to know. You might need some different kind of information about what this graph looks like. And to what this presents is an alternative take, an alternative sort of point of view. You can take the graph that the surface was presented to you as and say, you know what, I'm going to interpret that as being a level set. It's a level set. You can see so right here it says equals 0. It's a level set of this function down here called g, and then you can apply the calculus of level sets to this other function. And the calculus of level sets, as it turns out, gives you different information. And that different information may be exactly what you need. So it's a real slick move. Again, deceptively simple. Don't make the mistake, by the way, of forgetting that the function whose graph we were given is different from the function whose level set is equivalent. Right? F and g are different functions. F, for example, is a function of n variables, x1 through xn. Those are the only variables for f. G is a function of all of those and yet one more additional variable, y. Right? Very importantly, this is not the same function. It's not that different, right? The way it's written down on the page looks really, really similar. But it's an importantly different function with a different domain and, of course, a different formula. Okay. All right, so let's see an example. Suppose I am given this function right here, and I want to look at the graph of that function, which again, I form the graph by setting its output values equal to a new variable z in this case, arbitrarily. And I want to learn something about this graph. Now, of course, I can apply the calculus of graphs to this function. That will tell me some information. But another thing I can do, right? I can pull this move. This is the exact move from above. I can rewrite the equation. Now, again, nothing happened, right? Barely anything happened. Doesn't seem like this would be helpful, but I have now rewritten this as a level set. And so if I know the calculus of level sets, I can apply the calculus of level sets to this function. That will tell me completely different information than the calculus of graphs applied to that function. And also very useful. Now again, all this is, exactly what is the calculus of level sets and exactly what is the calculus of graphs. We're going to be developing that over the next couple of weeks. Yeah.
So, level sets are like, of a particular value, or like is it 0 throughout? Because remember we did 6 in the previous.
Yeah. So the term level set has a little bit of an ambiguity. Any given function has lots of level sets, and if you want to take a level set, you get to decide which level set you want to take. Here, I don't know, I just thought it was kind of convenient to just leave a 0 on the right-hand side. I suppose I could have added 7 to both sides of the equation. That's fine, whatever. But I don't know, why not have a 0? It doesn't really matter. But yeah, as long as your algebra is equivalent, right? You can add 7 to both sides of the equation, totally fine. Yeah. All right. Okay. Bad news. It doesn't go the other way. Every graph is a level set. And by the way, let me point that out, going back up to here. Every graph, right? Anytime you have an equation that looks like this, you can always just whip that one term over to the other side and always end up with stuff equals constant. So every graph is a level set of something. Right? Unfortunately, not the other way. Not every level set is a graph. Easy example. Here's a level set. Right? Level set of that function right there. But is this a graph? Tragically, no, because look, you can take that level set and draw a picture of it and just geometrically see this level set is a circle which fails the vertical line test, and this you just cannot write y equals a function of x. You can try, right? You can write y equals plus or minus blah blah blah. That's not a function. A function can have only one output for any given input, and that whole plus minus thing doesn't count. Yeah.
So in previous classes, teachers would say stuff like the graph of x squared plus y squared equals 1. Here we would just say, like, graphs only work for functions of x and y and vice versa.
Yeah, that it's a constant frustration for me that they use the word graph as a synonym for picture, which seems to me to be unnecessary. We already have a perfectly good word for picture. The word is picture. Right? So why do they need to make graph mean the same thing when we have this other distinct idea, what I'm using strictly speaking as a graph, right? And I don't know, I find that sloppy and it bugs. Yeah. You're right. It is a common usage, and I bristle a little every time I hear it. Yeah. Did that answer your question? Yeah. Okay. Is everybody happy with that? In fact, I think even our textbook does, in at least one place, refer to the graph of an equation, which, anyway. Okay. All right, moving along. Okay, so we're going to spend a little time talking about how to understand an equation of several variables. It was specifically 3 variables. Y'all know a bunch of examples of how to understand equations with 2 variables. Circles, hyperbolas, parabolas, ellipses, all that business, right? Various other curves that you can study. Like if it's a graph of a single variable function, you can use derivatives to understand slopes and concavity, and you can kind of plot curves, right? When you have a curve in 2 dimensions. Here we're going to try to understand surfaces in 3 dimensions. And it's another scenario where I'm not going to be able to give you the definitive, always works tool. There is no such tool. There's just various tricks and, tools for your toolbox that will work in different circumstances. So here's the first one. This is a lovely little theorem. If, this is a big if, most equations, this won't work. But if your equation involves x's and y's only as part of this special form, right here, square root of x squared plus y squared, if that's the only way that x and y appear, then you get this really powerful conclusion, and that is that your surface is rotationally symmetric around the z-axis. It's pretty awesome. Again, this is one of these low-cost, high-reward type theorems, which, of course, we obviously like. How do you check your condition? Eyeball. look at the equation. Look for where the x's and y's are. And if they're all inside of an expression like this, condition satisfied, right? If there's any stray x's, if there's a, natural log of y somewhere in the equation, okay, then game over, you lose, you can't apply this theorem. But sometimes, surprisingly often, x and y appear only in this special form. So, eyeball check, and then you get a powerful geometric conclusion from it. Yeah.
Is this like only if it's equal to z, or like if it's in 3 dimensions?
And yeah. So this is that's right for 3-dimensional equations. So equations that involve x, y, and z, and then specifically when x and y are only like that. Yeah. Okay. Okay. Let me try to persuade you that this is true. Let's suppose we have a point. And now imagine that I rotate that point around the z-axis, and of course that takes my point and it generates, a bunch of other points, including, for example, that point. And what can I say about these 2 points? Well, they're totally different points. They have different x's. You can see from the picture, totally different x's, totally different y's. They're different points. You wouldn't think that they would necessarily have anything at all to do with each other in an equation. But here's the neat observation. Rotations mean that the distance from the axis is the same. That distance from the axis, being r, is exactly what that is. Right? So these 2 points actually have the same value of that expression. And furthermore, and again, this is just the way rotations work, these 2 points have the same z as well. And now let's think about our equation. Yeah, they're different coordinates. X's and y's are all different, but the x and y only serve to compute this thing here. That's the only role that x and y play. And these 2 points produce the same result there. And they have the same value of the only other variable, so the arithmetic that goes into the equation is going to give the same result for both of these points. So either they both work or they both fail. And that makes this a rotationally symmetric surface. It's a pretty cool little argument there. Now I'm going to give you a different point of view, a different way to think about this. How would we convert an equation of this sort to cylindrical coordinates? And, cylindrical coordinates, everywhere I see an x, I'm going to rewrite that as r cosine theta. Everywhere I see a y, I put an r sine theta. But I don't actually technically have to do that. I can notice convenient stuff like this, and everywhere I see this, I can just put an r. Let the Pythagorean equation sort of work for me there, right? Everywhere I see this, I put r. That's the only x's and y's. By assumption, x and y don't appear anywhere else other than as part of what's going to turn into r. So there's no opportunities for thetas to show up then in the first place. And if your equation doesn't have any thetas in it, previously discussed, no thetas means rotationally symmetric around the z-axis. All right, is that cool? Yeah. All right. So the reason we care about this is this point right here. If you have a surface that's rotationally symmetric, you can generate it by looking at any cross-section, as long as that cross-section contains the z-axis, and then just rotate that single cross-section around the z-axis, and that will generate your surface, right? So just a quick picture. If you have, I need some space to work here. I can squeeze it in to here. If you have a surface that looks kind of like that, right? There's a surface that's kind of, it looks like a half of a sphere, right? This is rotationally symmetric around the z-axis. If I can find any cross-section such as, let's look at the cross-section here in the xz plane. I can take that cross section and then rotate it around, and notice that one cross section, when you rotate it around the z-axis, generates your surface. Neat fact about rotationally symmetric surfaces. So that allows us to actually generate answers to questions. So here we go. Let's suppose we're interested in this equation right here. By the way, this is the one from the previous page where I noted we hadn't technically figured out how to describe this equation yet. So let's do it now. How am I going to understand that equation? Step one, we observe that x and y appear only in the special form. Technically, okay, fair. There's a little quibble here. Where's the square root? Right? It does need to be square root of x squared plus y squared. Notice that's easily adjusted because I can just rewrite this as z equals the square root of x squared plus y squared quantity squared. And so, allow me, strictly, right? I mean, being super careful. And now x and y appear only in the special form, and that makes this rotationally symmetric around the z-axis. Is everybody happy with that? Powerful conclusion. It's rotationally symmetric. I don't have to wonder about the, maybe this is some weird lumpy surface that does different things in different directions. No, it's rotationally symmetric around the z-axis. I can pick any cross-section. By the way, there's my z-axis. I'm going to take any cross-section I want, as long as it contains the z-axis. I'm going to choose the YZ plane. No particular reason. Now, I could, if I wanted to, pick the XZ plane. Totally fine. Also contains the Z-axis. Good enough. If I really wanted to make my life difficult for no apparent reason, I could also pick some angled plane, like that. That just makes things weird. There's nothing to be gained from doing that. I wouldn't advise it. I suppose you could, though. Right? So anyway, you got options. Arbitrarily, I'm going to pick the YZ plane. The YZ plane is easily described as x equals 0. If I want to know what this cross section looks like, I'm just going to take that x equals 0, plug it in. This term here goes away. That means that my actual cross-section is described by just this one little equation, z equals y squared, and that's something I already understand. That's a parabola. All right, now rewinding, taking stock. We observe that this is a special equation. X and y appear only in the special form, rotationally symmetric around the z-axis. Next, I pick a cross-section. Arbitrarily, keeping my life simple, I pick the YZ plane, which gives me x equals 0, which gives me a new equation for the cross-section in that one plane, which I recognize. And then I just rotate it. Right? Again, the whole idea here is that you can just rotate the cross-section around the z-axis, and when you do that, I appeal to your geometric intuition. This parabola rotated around the z-axis makes a kind of a bowl, just like we'd previously claimed. Everybody buy it? Good thing to know, this is called a paraboloid. That's just terminology, but we're going to be using that terminology here and there, so heads up. Make sure you know that term, paraboloid. Now let me show you another example. Totally different equation here. How am I going to understand that equation? At a glance, I mean, just looking from the algebra, it's hard to figure. But x and y appear only in the special form. This is rotationally symmetric around the z-axis. Huge conclusion at a casual observation. Gotta love it. Next, now again, I get to pick any plane I want that contains the z-axis. Knock yourself out. Just to show that I can mix it up, I'm going to pick here the xz plane. Doesn't matter. You can use the yz if you like, whatever. I'm going to use the xz plane here, which of course means y equals 0, which I can toss into my equation, which makes my equation turn into that. X squared minus z squared equals 1. And flashbacks to high school algebra, does everybody remember their hyperbolas? Does everybody remember that there exists a thing called hyperbolas? You might be a little rusty on the details there. You're going to have to polish off whatever, dust off whatever memory you have of hyperbolas. This particular one looks like this. Make sure you're comfortable with that. If you're sketchy on hyperbolas, feel free to come in and talk to me in office hours. I'll be happy to help. And so again, here we are. We know the thing's rotationally symmetric. We know this is what its cross-section looks like. And now I just literally have to rotate this orange hyperbola, and geometric appeal, looking at the hyperbola, when you rotate it around the z-axis, it's going to make something that looks like this, which is called a hyperboloid. And it turns out that there's more than one kind of a hyperboloid, so this one, just for clarification, we call this a hyperboloid of one sheet. We'll see a hyperboloid of two sheets in a couple seconds here. Yeah, question?
Can you reiterate why the square root of x squared plus y squared means it's rotation symmetric?
Yeah, that's this argument up here. Two different arguments, I suppose. You can think about it in cylindrical coordinates, or it's this whole business about just looking at the 2 points and observing that they participate identically in the equation. It's a several minute presentation. You can just rewind the recording if you want to hear it again. But it's this whole business right here. Yeah. Okay. Third example. Now this one's going to be a little bit different. I'm going to appeal to your intuition that there is a similar argument that you can make if you want to talk about rotations around other axes. So everything that we've seen so far was around the z-axis. Well, there is a similar theorem about rotational symmetries around the x-axis, and a similar one around the y-axis. And I'm going to leave this as an exercise for y'all because I think this is healthy. I think this is good, practice. Look at this argument here, right? Digest and understand this argument. And as a test of how well you understand this argument, try to make the analogous argument around the y-axis or the x-axis. Yeah.
Could it also be like for any random arbitrary axis?
It gets weirder because
it would obviously be weird math.
Yeah, it's gonna. In all of these kinds of things, there's the question of whether it's worth the trouble.
Gotcha.
Right? And I think that might dip below the bar of being worth the trouble there. But yeah, you can always. There'd be a way to do that, but I wouldn't advise it. Okay. Yeah. Right. All right. Okay. So I'm going to acclaim. And y'all are going to supply the details. And again, if you get stuck, come to office hours. Happy to help. I'll help you fill in all these details if you'd like. I claim that when y and z appear only in the special form, that gives you rotational symmetry around the x-axis. Kind of believable, if only from a kind of a alphabet standpoint, right? Analogous roles and stuff like that. Okay, so this equation here, now again, notice it didn't really present quite that way, right? The minus signs make it look a little bit weird, but a little bit of rewriting, and check it out. Sure enough, y and z appear only in the special form, and so we have a rotational symmetry around the x-axis. So now again, take your favorite plane that contains that axis. You've got a bazillion options, and again, if you want to go crazy and do it with some angled plane like that, whatever. Again, I don't know why we would do that, right? There's nothing to be gained. But hypothetically, I'm going to pick this time the xy plane. No particular reason. The xy plane has an easy equation, z equals 0, which I can toss into my original equation, and out comes x squared minus y squared equals 1. Again, that's a hyperbola. Again, flashbacks to high school algebra. Make sure you're good at all that stuff, right? And that is that hyperbola. And now recalling that this is rotationally symmetric around the x-axis. And again, geometric appeal, but what happens when you take this orange hyperbola and rotate around the x-axis? And you get this kind of weird looking thing here. These orange hyperbola arcs, if you will, make, and I've never been happy with how I draw these, but it makes kind of something that looks like this. It's just hard to describe. Anyway. So now notice this is still what we call a hyperboloid because it is a rotation of a hyperbola. And so hyperboloid is a term that makes sense. But notice it's really different. There's two separate chunks that they call sheets. So that's why we call this a hyperboloid of two sheets. And this is a hyperboloid of one sheet. Right? Because in some sense there's kind of two different ways that you can rotate it. So different terms. Yeah?
So could you choose any axis to be 0? And in step 2 over there, could you choose any variable to be 0 and choose any?
Well, yeah, that's right. So you have a bunch of different planes that you can choose. I like to think of it geometrically, right? Don't think of it as what you're setting equal to 0. Think of it as you have multiple blue planes that you can choose that still contain the green axis, right? So the xy plane is what makes z equal to 0, right? If I wanted to use the xz plane, totally cool. Xz plane, fine. That would make y equal to 0. You'd get everything would kind of look a little different, but you'd get the same punchline.
So if we did the yz plane, we would get an equation of a circle, right? How would we work it out?
So now what you're doing is you're stepping off of the path, right? So what I'm describing here is a particular kind of argument that will give you a good answer. And what you've described there is, well, what if I go this way and bad things? Right, so if you stay on the path, then good things will happen, right? But I hear where you're coming from, but yeah, the whole thing just kind of doesn't work. Yeah. Okay. Yeah.
Wait, can you explain what's going on with number 1 again?
Yeah. So this is I'm just making the appeal, and I'm leaving the argument for you all to fill in the blanks. But when x and y appear in this special form, you get a rotational symmetry around the z-axis. I'm claiming that if y and z appear in the special form, that gives you rotational symmetry around the x-axis.
Like what has rotational symmetry around the x-axis?
The equation that we're trying to understand. Yeah. So there's a bunch of details to be filled in there, and that's what I'm suggesting as an exercise to think through. And it's analogous to the one we already did. Yeah. Okay, real quick, I want to throw some quick words at this idea. This is a really clever idea. Suppose you want to understand this equation. It's rotationally symmetric. Yeah, we could totally do it that way. Let's not. I want to show you a different tool here, right? I want to understand this equation. The observation I'm going to make is as follows. This equation here is super easy. It's a sphere, no problem, right? It's distance from the origin equals 13. Instant, just boom, effortless to understand that equation. That wasn't the question we were asked, of course. We want to understand this equation. So the observation I'm going to make is that the only difference here is that everywhere that there had been a z, notice I have replaced the z with 2z. And the question I want to address is, what does that do to the surface? If I make this little algebraic tweak to the equation, how does that geometrically deform the existing surface that I already understand into the surface that I want to understand? And the observation is, I'm just going to make a quick appeal that, that's a bad color choice. Let's see here. I'll use dark green. This point here, 3, 4, 12, that works in the original equation, obviously doesn't work in the other equation. That 12 is supposed to be squared. if I plug in 12 in for z here, well, wait a second, but in this equation I multiplied by 2, so the 2 messes it all up. But you can kind of account for that, if you will, by plugging in instead 3, 4, 6. The 6 goes into where the z is, gets multiplied by 2, becomes the 12 that in some sense it was supposed to be to make the arithmetic work, and again, everything works. So, punchline then, when you algebraically replace a variable with 2 times that variable, geometrically, your surface gets squished in the z direction by a factor of 2. Or to generalize, I'm out of time. Well, okay, you know what? I have to draw the line here. Anyway, this is going to end up being a really useful idea. We'll see you on Monday. Y'all have a good weekend. See you later. Oh, and as usual, of course, if you weren't here,